السلام عليكم. نبدأ اليوم محاضرة أخرى من سلسلة المحاضرات اللي قدمت سابقا من قبل مركز بحوث الطاقة بخصوص موضوع Integrated Reservoir Characterization of Oil and Gas Field. محاضرة اليوم راح يلقيها دكتور ويليام جودي. راح أعطي نبذة تعريفية عن المحاضر باللغة الإنجليزية، بعدين يتحول الكلام إليه ويقدم هو نفسه في تفصيل آخر إن رغب بذلك، وبعدين تبدأ المحاضرة. The title of the presentation today will be about digital rock. Okay, please mute all. Okay, so the presentation topic for today and tomorrow's lectures will be about digital rock technologies, including digital skulls. So the lecturer, Dr. William Goddy, he's a principal reservoir engineering at Halliburton, Brazil. He actually working now in the Rio de Janeiro's Halliburton Technology Center. He got his bachelor's degree in petroleum engineering from the Federal University of Rio de Janeiro, then got his master and PhD degrees in petroleum reservoir engineering from the same school. After that, he worked for 3 years in the Siemens company. Later on, he worked as principal reservoir engineer at Halliburton, as we said earlier. So on behalf of all of you, we welcome Dr. William to give us the lecture today.
Thank you very much. Thank you everyone joining this meeting. And let's just start here with our agenda, okay? Just a minute, please. Yeah. So today we'll cover the program one, where I call it's the introduction to digital rock technologies. Yeah? So we'll talk a little bit about our workflow and how we can move on dealing with digital rock, and also some experimental parts that can help us to identify our rock, our geometries. Move on to the basic concepts around this technology and the equipment and what we have to figure out about the methodology. And then we will show you 2 case studies regarding this, how we can reconstruct, how we can do some numerical simulation in the pore space. And tomorrow we'll cover the basic and advanced concepts, focusing on spatial core analysis, and then move to the core scale, what I call the new frontier, that we have a lot of new publications in the studies. And I will also show you some case studies, in this case from Ingrain, Middle East. But just before we start, I would like to brief you with a safe moment. Yeah? We just talked a little brief, started this presentation. We have this COVID pandemic here worldwide. So it's really important to keep ourselves safe for the infection. So it's important to wash our hands, use the mask, avoid contact with other people or a huge number of people, and be smart about our information. It's really important to go to reliable link to get this information about COVID. So you can go to the WHO website, World Health Organization, where I downloaded this folder. And of course, be kind and support other people, because we're dealing with difficult moments, not only regarding the disease itself, but also with the economics worldwide. So it's important to help people as well. So if you want more information, please go to the website that's there, and you can give more information about your region or how we're dealing with the COVID pandemic nowadays, okay? And then just before my presentation of the digital rock itself, I'd like to show you some reference that I really enjoyed and I read a couple in the last years. So I started with the book from Professor Martin Blunt from Imperial College regarding the multi-phase flow in permeable media. It's a really great book. I also have my hard copy with me, side by side with me. It's also important to keep in mind that we are dealing here with, we're discussing rocks and the fluid interaction, rod fluid interaction, but actually you can use a lot of this technology for permeable media, as I was mentioned before, paper and other materials. So move on to the second book here, is the Random Heterogeneous Materials from Professor Torquato. It's a really great book as well. You can find this kind of correlation between microstructure and microscopic properties. It's really, really interesting. And then two PhD theses, one from Dr. Tom Bultrace from Ghent University in Belgium, and the other from Professor Amir Raouf, that I have the pleasure to work with him and during my PhD studies from Utrecht University. So just put this for reference here if you want to discuss a little bit more about the reference and other materials, papers. I will put my contact in the last slide of this presentation, and you can contact me anywhere, okay? And then what's really important about digital rock technologies? Here we have, for example, in Brazil, we are dealing with a pre-salt reservoir that's a huge reservoir with a highly heterogeneous carbonate rock. And what's important about digital rock technologies? What I think is really, really great here is that we can do this kind of evaluation of the technology in different scenarios, and we can avoid the timeline that is necessary to perform some experiments. Yeah? So digital, actually nowadays we are facing this kind of revolution. Yeah? Every industry is moving to the digital way, digital sense of doing their work. So there's no difference from our oil and gas industry to other industries. So we are moving in this direction. Yeah? We are trying to understand our pore system. In this case here, I'm showing you some of our challenges. Yeah? Here's studies, and we select a region, and we did this, select some plugs. We did this kind of studies for thin sections. We can construct the plug here. We can check the pore system. We can see it is connected or not, and then we can do this kind of single phase and two phase flow simulations. And all of these steps here, it's related to what I call a digital rock technology. Yeah? I didn't write digital rock physics, because nowadays we are dealing with a broader sense of what is digital rock. Yeah? It's not only the physics, but it's a group of different techniques and numerical approach that we can do. So that's why we're calling it digital rock technology, not only digital rock physics, what we used to call, and you can see in different papers, okay? There is just to show you that we have several challenges regarding this kind of topic. Of course, we have huge opportunities. Yeah, we can really change the way we see the lab experiments. But as I will mention later, and we start to talk right now, we are not trying to just to stop to perform laboratory experiments and then try doing everything from a digital perspective. No. I think it's a really supportive way of doing the research today, or doing the service that we have. We can work with the lab to do this kind of quality control or checking what we are done, but to get some information about the digital, the pore system itself. So you see, I will talk not only about the digital way, but also with some lab experiments that you have to perform. Yeah? But as I mentioned here, if you have chance, we have a huge opportunity. So I think it's a really way to see the business today. Yeah? Then I will just start what we call the first stage of any digital rock evaluation. That is, we have to define a workflow. And this workflow, as you see here, I just put one of my workflow from my thesis, and we published it here in Interpore in 2018. It's just a way to see what we have to connect to get a good digital rock approach. In this case, I started with some laboratory experiments to give an overview about the pore system and the structure of the rock and the minerals. And it's really important because every technique that I put here in several boxes, they have some limitation. And I put here, you have to understand a little bit about we have this kind of limitations for each of one of these techniques. And it's really important to be aware that we have this kind of complementary evaluation. Once you, for example, we start to do this kind of thin section analysis and then move on to get the plug-in and then do the acquisition and microscopy, for example, all of these steps we have to stop and then think about it and see what we have to as a good approach, and then move on. So it's like you stop, you think, you do, and then move on to the next step. So workflow is really important. One here is one of my personal workflows, but you can find in literature several references, several different approaches. And as I mentioned, it's just not a computational or numerical evaluation, but it's also an experimental one. You have to define what you want to do, and then you have to move on. And of course, knowing that you have this kind of limitation when you go step by step here in this workflow. Just an overview, okay? I will try to cover as much as possible during this presentation, but of course, you have a lot of information. And of course, if you want to ask something specifically, please just ask me, and then we can discuss a little bit about a specific topic, okay? In this kind of here is just as I mentioned, I started with this kind of selection of the plug, and then I moved to this kind of acquisition with Microscopy X-ray. I will explain later what is it. Use some more experimental apparatus like pore-scale to get the porosity and permeability measurements from the lab. This kind of nuclear magnetic resonance or electron microscopy to check what you have there in our rock, and then we can do this kind of reconstruction. That's a really important step. And then you can do this kind of porosity analysis, and then you can move to the numerical simulation to get the absolute permeability, for example. And you have to be aware that you have this kind of issues related to the volume. When you think about micro simulation, you're dealing with a small volume. Then, if you have a workflow defined, we have to set every experiment that we want to do, or every measurement that we would like to implement or correlate in our workflow. And of course, as I mentioned before, you have different techniques and of quality control for each one of them. So here is just part of my evaluation with my thesis as well. You select the plugs, you go to the lab and you check your thin section, your sample, and then move on to the equipment that you can do the acquisition of the Microscopy X-ray images, and you can perform several other techniques. A good overview about your rock or about your pore system. And of course, you try to understand the fluid and rock fluid interaction, so you can go further to understand what we call a special analysis, a special analysis that we'll discuss later, not today, but it's a really important step as well. So here I would just to get your attention that it's really important to get a well-defined workflow, and then move on to what we want in specific equipments, checking every step, and then move forward. So as I mentioned, several steps, several techniques, some limitations, but of course, that's the workflow that we are following. So you have to be aware of every step and what you do. Once you define the workflow and the equipment that you're going to use, then we can move forward to the sample analysis. And the first step is a huge important step. So as I mentioned, digital rock is not about only numerical or digital approaches, but it starts with a whole gamut of different approaches. And one of them is the evaluation of your sample, of your pore structure. So we have support from geologists here in our office, or even in universities. We always have this kind of support from them to check your sample, to analyze your minerals in your pore structure, and it's really important. So I start with this evaluations, and then you perform some measurements. For example, porosity and permeability, as I mentioned before, it's a simple test. You can perform this in several plugs, and you have this like a value to do like a quality control of some of your own results during the digital rock evaluation. So I just two different approaches here. One is the traditional retrographic microscopy. It's a phase section analysis that you can see here. You have this kind of blue resin here to take a look at the pore system. It's important because sometimes you are trying to do this kind of differentiation between the rock and the pore system, and then with a good geologist, with your side side-by-side view, you can have a really good evaluation of your rock. And then finally, I just put here the skin electron microscopy. Now, here in this red box here, I perform this kind of evaluation, not only for electron microscopy, with EDS, the energy-specific X-ray spectroscopy, to check at least what kind of minerals you can find there in your rock. In this case here, I'm showing part of one of the samples that I studied during my thesis, and it's a cocaine sample. It's a calcium carbonate. It's CaCO3, mainly. And I performed several studies, several techniques in order to support the digital rock. So as I mentioned, the workflow is not only digital, but it also considers some steps in the lab. It's really, really important, okay? Now, the second one, it's what we call the basic imaging workflow, So what's the main idea? Once you select your sample, you have some information about it, you will perform this kind of acquisition using what I call X-ray microcomputer tomography. Of course, here, because you perform this kind of acquisition in what we call medical CT. I will explain a little bit later what's the main difference. But of course, it's one of the core equipments when we talk about the digital rock technology. It's somehow you have to translate what you see in the rock to a digital way. So we start with the micro CT equipment. Here's just a quick overview, the steps. Once we will do the acquisition of your images, or selected samples, you can perform the reconstruction. In this case, we are moving from a real rock, and reconstruct some slice here to generate a digital rock. And then finally, you can do this kind of image processing, and it's a part of the image analysis as well. And then you can take a look at your images, if they are okay, what the idea behind this part is to try to check if your sample or if your images, they can pass your quality control. So you can do some kind of post-processing the images that can turn the image sharper or can enhance the resolution or these kind of things. Of course, as I will explain later, there's a misunderstanding between resolution and pixel voxel size. That's the main unit in this image in 2D and 3D. But mainly the idea here is that you have to perform this kind of basic imaging workflow to get your images, and then to perform the reconstruction and later the numerical simulations. So then we have defined here this approach. We can go to the others. We have to perform the acquisition. It's really, really important. One of the things that you can differentiate between the medical CT, or I call it the micro CT, is that in this case, we can get images with a higher resolution when you use the micro CT device and micro CT equipment. It's not a regular one. When you go to the hospital, for example, you see what we call a medical CT. Is that equipment that you go there, the doctor can see the image, but then you have a low value for your pixel voxel size. So the image is not so sharp, it's not so clear. And when we perform the acquisition with a micro CT, then you can you get this kind of higher resolution image. But what the main difference between that? What is the source? The source of X-ray itself. One possibility is that you have this kind of nanofocus or microfocus. Depends on the geometry that you selected, you can get better or worse image. If you work with a nanofocus, you have this kind of ray flowing from a really specific real-time source. As you can see here in the image, you have this kind of better result. And if you work with just from micro, you have this kind of results. Of course, it depends on the size, the pixel or voxel size you're selecting. But mainly, this is the configuration that you have. Of course, that there are several differences between equipments, and you can have just one thing. I have to. Can you hear me? It's okay.
Yes.
Yes. Okay. Okay. So, okay, so one of the things here, you are working with this kind of nano focus or micro focus, yeah? So you have this kind of good, really good images, and depends on, of course, not only the source, but also the distance between the object, your cord, for example, your plug, from the detector. So what I'm showing here is that if you are changing the configuration between the source objects in the detector, you have different results, okay? So I just put this equation here to give an overview what I'm talking about here. If you're changing the distance between your detector and an object, you have a different magnification. So the equation here just showing that you have this kind of source detector distance here and source, just a moment, and source object detector as well. So if you have magnification, you have this kind of resolution related to your acquisition. So it's a really important step as well. As I mentioned before, spatial resolution is not the same. Is not the same as voxel or pixel size. There's a difference between them. When we talk about resolution, we're dealing with this kind of correlation. Okay. So again, if you're changing the configuration, changing the aspects of your images, yeah. So it's important to keep this in mind when you're doing the acquisition. And this is one of the important steps during the digital rock, yeah, when you have to set up your equipment, your configuration, and what the size of the pixel voxel size that you are working, yeah. So it's a really, really important step. And then just to give you an overview what I'm talking, when you do this kind of acquisition, what you're dealing with is the linear attenuation coefficient. It depends on the material, yeah, that you are evaluating. So I just put here the demand equation related to this X-ray measurement and the intensity that you are measuring, and put here what is given in Lambert-Beer law. So what you are measuring here is the intensity. Of course, you have this kind of you have the intensity here, what you get in your detector, yeah? But it's related to the linear attenuation coefficient. That's here, you can see it's exponential with a minus. So it's inversely related to your distance, yeah? And then this thickness of the object as well. So what I'm trying to form here is that you have this correlating the intensity that you get from in your detector, and it's decreasing the distance that I mentioned here. You have this, here's a negative exponential, yeah, indicating that the X-rays are attenuating when they pass through the object. So it's exactly what I showed here. If you have your object here, and you are passing your X-rays through it, it's related to the linear attenuation coefficient. But then what is really important. This is what we are measuring when we are performing acquisition with this equipment. So there are several ways to define source object detector configuration, and they will give you what we call a better or worse resolution. And here, just to give you what I spoke before, there's a difference between resolution and what we call pixel voxel size. When you see, for example, in a literature reference, an author writing about 8 and 9 micron, for example, they are dealing with pixel or voxel size, depends on the study. But it's different from the resolution, okay? So here, I'm just showing you, when we perform the acquisition, changing the configuration, you can have this kind of configuration. You can have, for example, if you have this linear red line here, object, if you do the acquisition with, let's say, a lower resolution, you get a acquisition with a higher resolution, here. have a really good result. So it depends also in the detector, as I mentioned before. And here is just to give you a brief view of the difference in the results. Yeah? If you go from the worst resolution to the high resolution here, you're increasing. For example, if you are working for 9 micron pixel size, for example, and then you are working for 18, you are double the size. It's exactly what you see here. For example, we have an 18 here, for example, 18 by 18, and then we move on to 9 by 9. So you're increasing your resolution, but you're decreasing your voxel size. Okay, so just to keep in mind that you have this kind of correlation. And of course, if you are working with this kind of high resolution, and if you're increasing the number of voxel size, for example, you will get more information from your rock than if you are working, for example, from medical CT, when you are working for high values for the voxel size, for example. Okay, it's an important step during the acquisition, because then all of your evaluation analysis you'll be focusing on these images. Okay. And as I mentioned, as the acquisition is related to the local attenuation coefficient, what we get from this data. Yeah? So as I shown here, you have this kind of gray value. Yeah? That's a local attenuation coefficient, but it's really strongly dependent on the atomic number. So if you have a high atomic number, you have this kind of higher contrast, yeah, between these gray values. So not only about it, it's also proportional to the mass density. For example, in this case here, I'm showing a coconut sample. It's a carbonate. And as you can see here, this part here is black. It's the pore system. Yeah? It's a pore, and it's mainly filled with air. In this case, yeah, we did this acquisition without any fluid. It's just air here. And the other part here is calcite, this matrix here. And also we have this kind of high density material here. And this one here is the parrot, yeah. So it's iron and sulfur, and you can see you have this kind of white material, yeah. So you can see that's directly related to the atomic number, to the mass density, and of course, when you perform the acquisition, we have to define a specific energy that we are using in our device. Yeah? And as I mentioned here, if you have a if you're increasing the energy, of course, more X-rays passing through your sample. So that's one of the things that here you can try to understand the different mineralogy based on your gray values. Okay. And one other thing as well, I didn't put here, but it's interesting. In this region here that we see here is a darker gray values. You also have a calcite. You have some kind of microporosity, or at least you have a material of more pore, with a persisting that's inside here. So you can see that's a darker gray, which is directly related to the local attenuation coefficient. Okay, so I think this image here can show just one of what we get from the acquisition using a micro CT device. Okay. Of course, as I mentioned, depends on the material and the atomic number. You have this difference in the image when you do the reconstruction. Yeah? Because what we get from the acquisition is a raw file. It's an image that you have to do like an invest problem to get these images here, well-defined slice. It depends on the atomic number and depends on the material that you're evaluating. You have in your sample. So here, just as an example, I'm showing some of the not atomic numbers, but the local attenuation coefficients related to different atomic numbers. Okay. So as I mentioned before, if you have iron here and sulfur in the parrot, you have these kinds of higher value of local attenuation, and then when you do this kind of post-processing, you have this kind of white material, yeah. So here just to give an overview about the different minerals that you can find there, and they are always related to the acquisition that you did, and then you can try to differentiate the sample, what you have in your sample. Yeah, and it's really important that you, what I mentioned before, you have to discuss with geologists and some experts as well about your sample, what you have there, the main minerals, and you can find this kind of undefined regions where you don't know about the porosity, or if you have this kind of, for example, let's say that we are working with sandstone and I have clays there. It's important to try to differentiate just from the beginning. Yeah, when you are looking at the thin section, for example, it's really, really important. And can give you some hints about what you can perform as analysis in these samples. Then, just to give you an overview, there are 3 micro-CT devices here that I could work in. All of them, they have this kind of specific setups. Some of them you can work with larger samples, some of them with higher resolution. Depends on what I mentioned before. Yeah, the geometry, the source detector, object geometry, and also, of course, the capability of the equipment. You can put, for example, 2 devices here, larger volumes. For example, this stromatolite sample here that you could perform the acquisition in this equipment, or a higher resolution for the whole plug in this other equipment. It depends on the manufacturer, your specification. But here's just to give you an overview that we have several different equipments. Some of them you can change the configuration, source object detector configuration, and can give you higher resolution images. Okay, so the equipment that you are working is also a really important step. You have to select one that can cover the pore size that you are dealing with. You know? And then we came to this slide here. This is really, really important. One of the main idea here is that we got this kind of images from the X. You see here that, for example, you have in the white region here is air, and here you have the material. As I mentioned before, it's correlated. Yeah, you can see this kind of pattern. Yeah, when you check the local attenuation coefficient and the image that you have here. Yeah, this we call a raw data set. It's not we have to do some kind of post processing to transform these images here to what we call slices. Yeah, and then if you can work with this slice and put all of them together, then you can reconstruct the whole image. So some of these equipment, they have a specific software to do this kind of correlation. Yeah, doing this kind of inverse problem to change from the raw data set to these slices here, and different software codes, for example, to reconstruct your image here. But as I mentioned, depends on the equipment, depends on the software. You have some scripts to perform this kind of construction as well. But what we saw before is this construct slice image. Yeah, but we got from the Microscopy. It's a raw data. It's it's raw. Yeah, you have to do some kind of post processing to get this slice images. Okay? It's important that the equipment, or at least the software that you have in your equipment, can perform this kind of transformation. Okay. In this step here, that's a further step. Is just you can use different software or different in-house codes. It's up to the researcher of the company. Yeah. And now, once you reconstruct your image, yeah, and in this slice pattern, then you have to perform the segmentation. Yeah, segmentation is a really, really important step. And when you are differentiating not only the pore system from the let's say a matrix, but also different minerals or different phases, let's call it. So we have several procedures. It's really important because when you perform this kind of numerical fluid flow simulation, you're interested about the pore system. Yeah? So we have to somehow extract the pore system from your rock. So segmentation is the step now. It's a process when you convert in these grayscale images to let's say a binary image, when you can, for example, differentiate the pore system from the rock. Yeah, once I saw a presentation, and the presenters told us that there's no poor or bad segmentation. If you do a segmentation that you can correlate with some of your experimental measurements, it's wrong segmentation. Actually, it's true. Segmentation, it's one of the most important steps here, but you can control it. Yeah, and there are several methods to perform this kind of segmentation. Yeah? And I will address some of them that you can. One of them, when you start to evaluate your sample, is try to understand how your histogram, your grayscale histogram, yeah? Because when you perform the acquisition, you got this image with several values of, several layers, several values of gray. It's a gray value histogram. But in this case, I'm working from 8-bit image, as you can see here. 8-bit refer to let's say you can increase the number of gray levels according to when you increase, for example, from 8 to 16 to 32 bits. And then you have, for example, when you have 8 bits, you have you have 256 possible values. Yeah. When you work with 16 bits, you have more than 65,000 possible values. So we're increasing the number of levels here, and they give you some hints about your distribution, about the distribution of your pore and rock. Yeah? And here I'm showing you a histogram and some of the Gaussian that is you can evaluate from this histogram here. Yeah? And in this case here, you can use some free software or in-house codes. It's up to you. I use tools, open source and one free software. One of them is FudgeJ. Yeah, we can correlate this kind of image and the histogram, and the other is FITIC here, that you can evaluate the Gaussians when you are looking at your complete histogram. Yeah? And some segmentation procedures just use this kind of cross between what we know that's a material, a matrix distribution, and what we know that's pore distribution. In this case here, this first one is the pore system, the last one is the material, and you evaluate this cross between them, you get a value that is the threshold value. Yeah, at segmentation, you can perform segmentation just based on this value. Of course, it's a simple approach. You can perform this, as I mentioned, with free software, for example, if you have this Microscopy image, of course. But the histogram gives you an overview. If you have this kind of simple one model or bimodal distribution, and gives you some hints, some ideas about your distribution, not only the pore system, but also in the minerals and the phase that you have in your rock. But as I mentioned before, you have different segmentation methods. I try to differentiate them based on the four main ideas. And one of them is manual segmentation that, for example, is based on the evaluation of thin section, or for example, you can perform this looking at the results from SEM analysis, or you can do this kind of evaluation based on a histogram. Yeah, you can evaluate different Gaussian curves. There's a second one that I call a semi-automated one. It's also based in histogram-based segmentation, but you can perform like in a post-processing to get better results, to try to identify other features in your image. There are several automated methods. I will describe some of them later. And there is a last one that I call nuclear magnetic resonance-based segmentation. I will explain a little bit later. And all of them, they are really important because you have to really differentiate your rock, your pore system from your matrix, let's say, in a good way. So we start with segmentation methods based on automation procedures. I just put here this table. It's from the work from Seijin and Sankur from 2004. It's a really it's an excellent reference. The authors, they selected 40 different non-destructive segmentation procedures. We call like entropy and so on. I tried several of these segmentation procedures. I put a red box here in the 5 that I tested with automated procedures. Okay, and some of them is based on local distribution of the gray levels. Some of them try to understand these like a clusterization of the values. Depends on each approach. Okay, if you're interested in different automated methods, please take a look at this source here. It's reference material, and of course nowadays you can work with different scripts to perform this kind of evaluation. There are several codes from Python, MATLAB, and so on. And also there is an approach from using machine learning. You can try to identify these different features in your image and try to perform this kind of automated procedure, segmentation procedure, based on images, just with this kind of supervised evaluation using machine learning as a really important technique. Okay, as I mentioned, I separate 5 different automated procedures here, and I'm going to show you here the results. Okay? All of them are performed using, in this case here, MATLAB codes, but of course nowadays you can have access to Python codes doing this kind of evaluation. So I started with the gray level image here, the gray image here from the Microscopy after the post-processing, so it's not a raw data, it's just constructed image, and then I perform different procedures, and I got this kind of result here. Of course, I didn't perform specific analysis for each one of them. I just put some of the default because some of these methods here, you can change some parameters there, try to enhance your segmentation procedure. And as I mentioned before, it's important to try to do like a quality control during your segmentation procedure because this is the first step to separate your pore system. And if you're doing this in a wrong way, you will get for sure wrong results. So it's good to keep in mind that you have to follow a good segmentation procedure. One of the other that I call semi-automated, I use in this methodology here that's called active controls without edges. So the image, the code is looking for this kind of pattern, this kind of boundaries. And then once you have this kind of boundaries here, defined boundaries, you can do this kind of processing to check if you are considering the main features of the image. So it's not completely automated. You have to do like a post-processing control, with like a user control. Of course, if you have a geologist with you, work with you, it's easier to identify these different features. And this is what I call a semi-automated procedure. It's a really interesting one. It's a code that was in MATLAB as well, but probably you have several different scripts nowadays, even in Python. And I encourage you to take a look at these papers here in this reference. Then I would like just to give a brief overview of what we call a nuclear magnetic resonance based segmentation. A quick overview of the NMR technique. That is a phenomenon that occurs when you have this kind of atomic nuclei in a magnetic field, and then you are exposing your material to a oscillating magnetic field. What occurs in this part? You have this kind of magnetization vector, and then you're changing this when you move when we're changing the magnetic vector, you're changing the direction. So what I try to explain here in this slide here, this a really brief, a really quick overview of the NMR technique that we can use for the digital rock evaluation. So once you perform this kind of energizing pulse in your sample with a specified duration, you can change this pulse with a 9 degrees angle clearance, and then we get what we call a free induction decay. I'm not trying to explain the whole technique, the whole methodology, because it's an entire field of study. But the main idea, when you identify this free induction decay, FID, for each FID that you have a on-time constant that we call a T2, that's a transverse relaxation time. And this parameter here, even call it, we can also call as relaxation time. This one here, we can correlate to the radius. And what's the main idea behind it? The main idea that you can correlate according to a simple equation, and depends on the distribution, the T2 distribution. We have this kind of small to larger pores. And as you can see here in this image, small pores, you are closer to the origin, and you are moving in opposite direction when you are dealing with larger pores. And then we can correlate the T2 distribution that we got from the NMR, and then we can correlate to the radius using this simple equation here. Of course, you have to understand and approximate some steps here in this first equation here. But what I try to show you, that you can correlate the radius that you have for this pore radius here, pore radii. You can correlate to the distribution. In this case, where we did a study performing this kind of evaluation, and of course, there's a parameter here, a constant here, that depends on the geometry. In this case, let's say that you are working with this spherical shape here. So if you're considering the pore system as that is fulfilled with spherical pore distribution, we can consider the constant as 3. Of course, this number can change according to your geometry. But let's say that you have this kind of pattern here. So you can correlate, but then you have to deal with this constant here that we call a transverse surface reactivity. It depends on the material. So it's a really important step also if you are dealing with NMR-based segmentation, to try to get the real result here, the real value for this activity here, because you're going to use this here in this equation. And if you plot this here, what we get from this correlation between radial and T2 distribution? We have this kind of image graph here that you are seeing. So we are performing the evaluation. We are measuring this, transforming for T2 distribution that you are seeing here, for small pores to larger pores, and then using the equation, we are changing this to radius. So it's important because one of the quality control steps that you can perform during the digital rock evaluation is the size of the radii that we are dealing with for each different sample. So in this case here, I'm showing here with this here that if we perform acquisition, let's say with 10 micron voxel size, we're losing this kind of information here in our image. It's not possible to check this sub-resolution porosity, as we call it, okay? So, as I mentioned before, every methodology has its own limitations, In this case here, there's the limitation, of course, of the microcity acquisition, also the limitation of the reconstruction of the range of pore radii, okay? It's part of the limitation for, in this case, for this specific methodology. And then, of course, if you have this distribution here, you can correlate, you have this kind of more pores in the more larger pores than small pores here. You can see the peaking, and you can perform several analyses. This is one of the procedures that you can correlate, not only with segmentation, but also with distribution of your pore radii, your pore size distribution, what we call it later. Here's just to give you, again, overview. You have this kind of resolution porosity that is here. For example, in this case here, I'm showing a real case when we performed the acquisition with 10 micropixel size. So we could evaluate 5 micron as the minimum radius, okay? And then we are losing all this information here. So we're trying to check your cumulative porosity directly from this technique. You can at least define what you are losing. Yeah? So I'm just trying to show you here that you are using 2 different techniques, for example, NMR or Microscopy, and you have this kind of cutoff between super resolution, for example, Microscopy. Of course, if you are defining a pixel size here or voxel size, let's say, it's at 10 micron, and you have 5 micron as your minimum radius, you can find anything about this region here. So we call this a super resolution porosity. There are some different definitions about microporosity, super resolution porosity. Depends on the technique, as I mentioned before, but also depends on your equipment. And for example, this part here, I'm using the definition from the NMR to do this kind of off between macro, meso, and microporosity. Here, using the Microscopy acquisition, I'm just differentiate between frequency using this approach. Yeah? So it's the main difference between the porosity and what they call super resolution porosity. Here is a real cooking sample from my thesis, and I work with the guys from the lab. And as you see here, we have the distribution, and we can infer the porosity value that we get using Microscopy images. Yeah? Here's one possible segmentation procedure in this case. And other technique that we are using in this case, again, to check distribution, the radius distribution, is the MICP, yeah, the injection capillary pressure. In this case, you have your sample, or at least a piece of your sample. Yeah, you can use this kind of lower and higher pressure chambers, and you are using mercury to perform the intrusion of this mercury inside your sample. And as is not, I will mention this. I will talk about it tomorrow about the two-phase flow simulations and experiments. But in this case, it's a good way to control, because mercury have any kind of material, for example, in your rock, that's mercury wettable. Yeah, there's no correlation between the surface of the rock with the mercury. So it's good to perform this kind of evaluation using mercury to check the distribution of your radius. Yeah, and then you can generate this kind of curves that we call a pore size distribution. This one here is a cumulative. So you are increasing the pressure, and you see that you are. We can evaluate smaller radii in this case. And here is a pattern that correlates with this kind of experiment. Yeah? So we are pumping pumping the mercury there, high, increasing the pressure, and you can see that you are considering smaller pores here, and then you can perform this kind of cumulative distribution. In all slides, you have the reference there. If you can take a look at the site or the papers, okay? And then I can send you later if you're interested. And once you perform this kind of evaluation, you have this kind of distributions here. One here is from one of the works from Ingrain Lewis, from one of our consultants here. It's a lab experiment. It's an MICP from the lab. Yeah? It's not a numerical MICP. I will show you later that you can perform this kind of analysis. This one here is performed in the lab, and you can see that the authors also separate in different regions. Yeah? Micro, meso, and macro porosity. And some of them you can also take a look at the pore size distribution here in red. When you take a look at the peak here, you have an idea where is your radius, or at least the maximum number of pores with that specific value of radius. Okay, the same thing here. Okay, for this one, and the PDF now, the distribution is the cumulative distribution, and then you can see that we're covering all the possible range of pore size distribution here using mercury. It's important because one of the things that digital rock can do is perform this in a numerical digital way. Yeah. So here I took this here also from Ingrain, and it's a mercury injection capillary pressure experiment. And in black you see the red line here, the black line here, the experiment, and then the blue and the red ones perform this numerically. But how we perform this numerically? We have to select specific regions here that are covering this different radio distribution. You see here that you have this kind of larger pores here, and in this one here, this region, we have this kind of tighter region with smaller pores. So we can perform this evaluation here. The blue and red ones are numerically, okay, within House code to perform this kind of correlation between the mercury injection pressure, capillary pressure experiments and the numerical one. It's one of the things that, one of the quality controls here for this rock, for example, and then we can check if our selected samples, selected subsamples here from this larger one, they can give us some hints about the distribution of this sample. And then this, there's an important topic, yeah, because we are selecting smaller regions here to perform this kind of evaluation of the distribution of radius. How can we perform the reconstruction later? Yeah? Once you get this kind of information, when you perform this kind of quality control. Sorry, this one here, there's a movie, but just a moment, please. It's a movie that I reconstructed in one of my thesis samples, and then you can take a look at the pore system, some of the high density material as well, some of the specific. You can perform this in different ways. You can do this kind of 3D reconstruction using some scripts in Python, MATLAB, or other language. It's up to the user. Yeah, you can have this kind of free source to open source software. I put some of them here as a reference. You can perform this kind of reconstruction using commercial software, Visual, ScanIP, Firefly, and you have different software nowadays to perform this kind of reconstruction. Here I perform using Naviso, okay, and it's a really it's a small subsample. It's a subsample from my cooking sample that I showed before, yeah, the plug that I showed before. And once you can reconstruct your sample, you can take a look here at the distribution of here, the histogram, everything you can infer from your image, yeah, from your model. But then it is one other question. Is this volume representative for my numerical analysis or further evaluation? This is a really important step. And then we have to take a look here carefully about what we call a representative elementary volume, yeah, the REV. What is the REV? REV is the volume that you can, once you, just a moment, yeah. The REV is the volume that you select to perform this kind of evaluation that could represent your rock, your pore system. And here I show you a simple graph. For example, if you're dealing with really small volumes, for example, or you can just capture, let's say, a grain here, or just a huge pore system, and you see that your petrophysical property is oscillating. If you are changing this volume, let's say, you're dealing with the red one here, the smaller one, and the blue one here. This one here has a huge, for example, permeability. Yeah? This one here has a low permeability value. So you see that you have this kind of oscillating pattern here. And you just get this kind of stabilization to reach your REV. So REV depends on the property that you are evaluating. It's a really important topic here. So for example, you can get REV based on porosity, for example, that's different from your get from the permeability. It's one of the things. But not only this, it's also related to heterogeneity and scales. I took this image here from the Professor Corbett's presentation, showing how these scales changing the RDV. Yeah? If you are moving from micrometer scale to 100th meter scale, you have kind of different RDVs for each sample, for each of the scales, and you have to correlate each one of these scales here based on different procedures. And you can see tomorrow some of these upscaling procedures. But it's really important to have in mind, to keep in mind that you have to perform all your evaluation based on the REV. Okay. This is a brief review of the work from Vic, that he performed some of experimental measurements of the REV. Yeah. So he did this kind of evaluation of porosity and also in permeability. And you can see here that if you are changing the physical parameter, you can change your REV. Yeah? Just to give an overview, this is an experimental result, okay? And then we also performed the numerical one. Yeah, during my master's, I could work with this kind of evaluation of REV based on the numerical simulation of permeability, absolute permeability. And then I performed this kind of study here, the methodology, when I cropped the sample in several other smaller volumes and simulate all of them. This one here is finite element methods. I'll describe method later, but mainly I got this kind of convergence of pressure and velocity, and I could calculate the absolute permeability and also the porosity. Yeah? And it's a direct application of digital rock technology, for example. You can infer your REV, for example, based on this kind of, I'm showing here, just a comparison between experimental measurements and numerical ones, that it's the possibility to perform this kind of evaluation without cropping, without cutting or sample. Yeah. Here in this case, the authors have to cut the sample. Yeah. In smaller volumes, you have the larger volume here, and start to cut the sample. It's it's a destructive method. Yeah. But here it's a digital cropping. Yeah. You are just selecting some regions, as I showed before, and based on these regions here, you can perform this kind of cost evaluation, permeability evaluation, and it's one of the gains when you do this kind of digital rock evaluation. It's not necessary to cut the sample. You can perform this in a relatively fast timeline, which is really great. That's one of the things that digital rock is really good. Yeah, you can reduce your timeline during your project. Yeah, because you can have some hints, some ideas, some results faster than the experimental measurements. Yeah? Which is really great. Yeah. And then, as I showed before, I did some computational experiments there. But what methodology, what methods we can use there to perform this kind of numerical fluid flow experiments? I separate three of them, yeah, to three main groups. The first one is the direct pore-scale modeling. When you have this kind of flow modeling, solving Navier-Stokes equations directly on in the boundaries, in the complex boundaries, in a 3D representation. One of the most well-known methods for perform this is the Letts-Boltzmann method. Okay, I will explain later each one of these. The second one is the traditional computational fluid dynamics, CFD, what is commonly called. It's a class of methods that you are using a traditional mesh-based to represent your geometry, your boundary. Yeah? For example, you can reconstruct your geometry of your pore system with these meshes. And there are three main possible methods here, what we call the finite difference, finite volume, and finite element methods. Okay, I will try to get some of the main ideas of one of these here. And the last one is the pore-scale modeling, what we call PNM, pore network model. It's a representation of your pore system geometry, for example, and we are generating pore bodies, what we call, and pore floats to represent this connection between larger sections of the pore with this kind of pore floats, yeah? This capillary pore system. Okay, you try to get some of the main ideas behind each one of them. First one, Let's Boltzmann. Let's Boltzmann is well-known methods. It's one of the methods that you can parallelize the solution with. Can give you a really great impact on time of your simulation. Yeah, it's based on microscopic models. Yeah, so you have this kind of kinetic equations that you can incorporate not only the fixed or the microscopic phenomena, but also the mesoscopic phenomena as well. So here I'm trying to show you some of the representation, because one of the ideas is to you have to think that is a method when they are creating this kind of fictitious particles we call like mass fractions, and then you are propagating, colliding with each other particles in a regular lattice that you are defining. So the main idea is to have to represent the stress tensor correctly, and this is one of the things that you have to generate this lattice based on some well-known correlations. And then I put here that this one here is one of the examples. It's a 13 particle velocity direction corresponds to a 3D unit cell. And some of the Let's Boltzmann methods, they use in different approaches. Say, not only 13 particle velocity directions, but also 15, 19, 27. So when you see this in reference, for example, you know what kind of geometry or what kind of pattern they are creating, okay? And as I mentioned, as they are considering this kind of fictitious particles and they have this kind of propagation and collision between them in this regular lattice that's here, yeah? One of the things that you can define is the boundary conditions, yeah? For example, in this case here, I'm showing that you have several nodes, yeah? Each of these nodes, it's you have like a particle velocity vector defined, yeah? And then, for example, in these gray regions here, you have the boundaries of the rock, yeah? It's back in the nodes here. And then, for example, you have this one here, to your first one. You have some of the directions that you can perform with your particle. And in some cases, for example, it's not possible to perform this kind of interaction between your particle and the boundary of the rock, for example, what's the grain. So the main idea is here is to correlate kind of the simulation here for each time step. You're propagating this kind of collisions, and the velocity that you have here, you can then in the second step correlate and recover the Navier-Stokes can be solved based on this kind of velocity profile that you get. Of course, you have some kind of limits. You have to define, for example, in this case here, I wrote that you have to perform these incompressible limits to keep in mind that you are solving the physics behind the correct physics behind your problem. Yeah, Let's Boltzmann has been used for a while. There are several different methods. Ingrain use this kind of methodology. It's really great. You can do a lot of things, a lot of higher performance computations using these methods. But of course, we have different ones. The other one is the computational fluid dynamics, as I mentioned before. And then you're generating this kind of mesh to represent your system. Here you can see a geometry, yeah, the persistent geometry that was generated, in this case here with a finite element method, but just to give an overview, what we call a mesh. Yeah, some of them are structured, some of them are unstructured. This one here is unstructured grid. In this case, some here you have more elements than the others. So it's one of the difference between the three different methods based on CFD. Yeah, the first one I wrote here is the finite volume method. It's a well-known method. Okay? You have this kind of control volume, and you are trying to integrate the maximum moment balance equations from Navier-Stokes or Stokes flow, for example, in terms of fluxes. Yeah? So when you have this, you have to define well your boundaries and also the neighbor. Yeah? So you have this kind of volume here, you have the neighbor volume, there's interaction between them, and you're going to solve for each time step a partial differential equation that is related to this fluid flow. But in this case, it's interesting because you have these algebraic equations and you can correlate them and can solve them numerically. which is really great. Yeah? I put some other reference here. I can send you later. They are really interesting. This is based on finite elements, okay? And sorry, in volume, finite volume. And then I put here some difference between the finite element volume, finite element methods, and finite difference, okay? The first one, the finite element methods, it's you have to define, you are discretizing the various equations again in a mesh-based boundary, yeah, with several nodes, but with a finite number of nodes. And then, based on it, you can create this kind of irregular geometries, you know, which is one of the main difference between this and the difference methods, because it's really hard to work with this kind of persisting geometries. They are really heterogeneous, and so finite elements, it's a good way to understand and try to solve some of these problems. They have some correlation with the finite volume, yeah. So you are creating this kind of domains there. You have this kind of finite elements connected to each other for this kind of nodes here. You are solving some specific equations that we call you have an unknown function that is ranging between your whole boundary, but you have to specify these specific finite elements and solve algebraic equations for each of them. And then you can have a good result for the entire problem. That's a way to do this, okay? Finite elements, a different field of study as well. There are several possible field of studies for this. I think it started with the space industry, aviation industry, sorry. And you can perform a lot of different numerical solutions, not only for laminar flow, but also for turbulent flow as well. The last one here that I mentioned is the pore network modeling. Yeah? So I try to reconstruct your geometry based on this kind of bodies here. I'm showing you red, and kind of flows here in blue. Yeah? So we're connecting these larger pores that we call a pore body with this kind of flows here. And this is a simplification, of course, but it's really interesting because you can generate a lot of information of distribution, and not only of the pore bodies but also the pore slopes. Yeah? You can try to compare with the MICP, for example, NMR distribution. And here I'm just showing you one of our cocaine samples reconstruction based on PNM, yeah, and the pore radius here, as you can see, it's a simple reconstruction on shears and floats here connecting all of them. Yeah? I just here also some of the simple equations that you can work with the PNM approach, okay? I'm not go further in the equation, those kind of things. I think the presentation is to give an overview, but as you can see here, to perform the single phase fluid flow simulation, yeah, to get the absolute permeability, you can solve this kind of equations for the float and the correlation and the connection then with the pore bodies. And then later you can apply like a Darcy's law to get the absolute permeability values. With this information here, I'm trying just to show you briefly the methods. I just show you some of the pressure convergence here that I got from finite element methods and PNM-based methods. Okay, just to give an overview of the pore system and the kind of results that we got. And then what we can do performing this kind of numerical analysis, several analyses can be performed. The first one, of course, is the porosity. Yeah? Porosity can be related with the reconstruction. So you have your voxel size as a pore, you have the total number of voxel size. You can get a direct correlation, and you can infer or estimate your porosity. Not only the total porosity, but also the connected one. Yeah? You can perform the simulation for absolute permeability, as I mentioned, formation factor, elastic properties. You can get pressure and velocity profiles. You can study tortuosity, the distribution of your radiant, yeah? What we call the pore size distribution curves. You can try to create some kind of permeability, porosity, K5 trends, and see if you have this kind of pattern in your sample. It's a hope that there's a huge number of possibilities dealing with digital rocking technology. This one here is just to show you a velocity file that we can get from the numerical evaluation. Okay. In this case, I'm using again a finite element method to perform this one. But as I mentioned, there are several possible methods. Let's go to finite element methods, PNM, based on PNM. And what I think that's really great here, what we get from this numerical analysis here, that you can do this in a really fast timeline. This for sure, because nowadays we can work with powerful computers. We can, for example, let's Boltzmann, you can do this kind of parallelization to perform even faster simulations. So you can use a cluster. It's a whole new world nowadays. You can perform several of these analyses in a really fast timeline. What I think is one of the main goals using digital rock approach. Okay, then I just show you some of case studies, really, just to give an overview what can be done. Yeah, this one here I performed during my PhD studies. I select coquina samples that probably you saw before, and then I performed some kind of SEM EDS analysis to give an idea the difference between some regions here. Some of the regions you have this kind of unresolved, some of them you have this kind of quartz, and then you have to understand a little bit better, not only the material, but also the pore system that you are trying to recreate, to reconstruct in a digital way. So I start with a simple sample here. Yeah? I perform this kind of lab experiments, and then using a micro-CT of this specific red box here, I could perform the micro-CT acquisition of different voxel size. This first one here is 6 and the other is 9. And you can see when I perform the reconstruction until get the PNM, for example, I'm losing some kind of information. Because here we are not covering what's from 6 to 9 micron, and here we can cover. So you can see that we can connect some regions that were previously disconnected, which was really interesting because it's one of the things that you have to keep in mind is that you have to select your equipment. Yeah, you have a configuration, you have this kind of geometry between your sample, detector, your source. You have your image, but then you have to be careful about your limitation. As I mentioned, some of your pores you're not seeing. You can consider them during your simulation or during your evaluation, digital evaluation. Okay, and here again, just to show you what we can lose information of the connection between the pores, and we perform this kind of evaluation, the distribution as well. This one here based on PNM, and we could take a look at this, the pore body and pore flows distributions. When you're changing from one resolution to the other, what are we losing, what we are not considering in our model. These parts, they are really interesting. But in the end, what I would like to get to is the results for the whole plug. Yeah? In this case, I'm showing you 3 different results on 3 different micro-CT equipment configuration that gave me different voxel size numbers. This one here, I work with 9 micron. This one here is 18. This one here is 25. We're seeing that I'm losing formation when I reconstruct the pore system. And I perform the absolute permeability simulation here. You can see the pressure distribution here. And here's man of here that you can work with this kind of multi-technique. Yeah, and I explained before. You can perform this kind of thin section analysis. You can perform the micro-CT acquisition. EDS, for example, you can correlate with values from pore perm from the lab. Yeah? So I try to compare the results here in this paper with the measurements that we got from the lab. It's a pore-scale perspective. Yeah? We are trying to reconstruct in understanding the geometries that we have. Of course, it was a numerical study based on this kind of reconstruction. I work with subsamples and also with the plug scale. Yeah, so I would like to understand what was happening in the pore scale, but try to correlate with the whole plug, yeah, the entire plug. And it was, of course, no PNM method, okay? As I mentioned before, you can perform these different techniques and different methods, computational methods. And the last one here is a work from Zambrano. It's a really, really great case study because he worked with different samples. You can see here the scale now, but he used the electrical approach. He performed this kind of multi-resolution acquisition, which was really interesting. He tried to get the image of a higher resolution, less than 2 micron, for example, per voxel, until worse resolution, let's say, now, with higher values of voxel size. They also performed some kind of experimental analysis, similar way that I did, but he did it before, of course, in 2018. And he also performed this kind of numerical analysis, studies. So he copied this kind of regions here digitally, after the acquisition, and he could perform this kind of simulations as well using let's Boltzmann methods. He could also understand what is going due to the problems with the volume, So he could explain a little bit about the REV because he tried to generate some results based on smaller volumes. The volumes, of course, they have to be representative of the whole sample, or at least the region that you are studying. And as I mentioned before, he will try to understand some of the issues related to the forming porous carbonate grainstones. So in this case here, just to show you briefly some of the results. Of course, these values here is the size of the volume, the cuboid that the authors selected. So you have 400 by 400 by 300. So sometimes you are not being, you are speaking not only about the size of the sample, but the number of voxels in each direction. So as you can see in the Z direction, you have this kind of larger volume, but they have to crop in different regions according to the phase that you have, to the minerals in the pore system as well. And then to give you a really quick view of some of the results, you see here permeability LBM is let's Boltzmann simulation, and the other here, for example, is Karman. So he tried to correlate both of them. He tried to correlate the porosity with the permeability. Both of them, they got the results from the digital rock perspective. Okay, the tortuosity as well. So a lot of possible analysis, evaluation that can be done using the digital rock technologies, or at least the approach. It's as I mentioned before, it's a really great multidisciplinary way of seeing the rock, the correlation between rock, fluid, and fluid rock as the whole system, using different techniques, different equipment. It's really great. And just to finish, I think it's time. What I want to talk about this method, this digital rock technology. It's I don't know, but it started some time ago. Let's say I had some publications from Professor Bluntz from early 2000s, but they are still in development. We are still in the edge of the technology and try to push it forward. It's as you saw, we have a lot of methodologies. We have different techniques. We have to correlate all of them. We have to specify some of the limitations between these techniques. It's a lot of information and steps that you have to perform until you have this kind of results. But they can be performed in a fast timeline that I mentioned before, which I think is really, really great. You can perform this kind of sensitivity analysis. You can change you can select different regions of your sample. You can do this kind of digital crop. So you can perform this kind of REV evaluation. In my opinion, a lot of things will happen in the next years regarding this, not only in the micro in the micro scale, but also in this kind of correlation to the macro scale. This kind of upscaling procedures that you can go from the pore scale to the core scale. I will address this in the next presentation, but just keep in mind that it's really important to select this REV, perform this kind of evaluation, the simulation that you want, and then do this kind of process post-evaluation, check if it's okay, the limitations between each step, and then you have a really good result. You can see there are a lot of literature, a lot of already published material. All of them that I put here, the already published material, you can find different results. Some of them, the results are not so great, but some of them start to talk about specific issues that they found, and then the other authors found some solutions. And that's the way Digital Rock is working. Yeah? Every day we are starting developing a new way to think about this problem and how to solve these problems. And I think it's the future for the industry. The digitalization, in this case, a real digitalization of the rock. It's a real way to go further in our studies, mainly for the oil and gas industry. Okay. I would like to thank you all. I think it's time. Yeah? If you have some questions, I can give some references as well.
Thank you, Dr. William, for your nice presentation. Actually, yeah, it's time open for questions. Anybody has questions, he can answer directly.
Sorry, I put my headphone because to listen is better with the headphone, but I can't turn off it and then talk with you. Okay.
Yeah, actually the voice wasn't that good most of the time during the lecture.
The sound is not so good, yeah?
Yeah, I think if you use cell phone, maybe better. How's the internet signal there in Brazil? Is it like fast?
Yes, but sometimes we have this kind of problem with the connection, oscillating. Yeah.
Okay. Anybody has question? Okay, for the sample that you have taken and to make pore network analysis, were you able to get the sample from autocrop?
Can you repeat, please? If you can get the samples from the autocrop, yeah?
Yeah, can you get it from the autocrop and do your analysis on CT microscopic images in order to get the resulting properties such as porosity, absolute permeability, and other properties?
Yeah, actually, to perform this kind of evaluation, you have to get the plug, or at least see some subsamples from the plug, okay? But for example, in the first slide of the presentation, I select a region. Now I took an outcrop, and then I plug in some samples, and I perform the evaluation. But you can perform some other evaluation analysis with the whole core using the medical CT. In-grain has this capability. I'll show you later, actually tomorrow, about this capability. But you can perform the whole core, okay? But even though you have to select some regions, but the digital analysis can give you some ideas why you have to select the best plugs. And then based on this pre-selection, you can move forward in your analysis, okay?
Okay, so the resulting phi and k from the CT image, how accurate in comparison with the same measurements from core analysis, from the routine core analysis?
For example, for a plug, yeah, you're mentioning.
Yeah.
Actually, it's perfect. I can tell you that absolute permeability porosity, you can reach almost the same value, okay? Because this part of the technology, it's already well known, well established. So you can calculate porosity with no problem at all. Absolute permeability, as I mean, for example, in this case here, let me see. Just to show, come back. In this one here, I could evaluate absolute permeability, and I did some comparison with the real pore measurements. And with this one here, that is a higher resolution, I got almost the same value using PNM. So if you are using fine element and let's Boltzmann for sure, you also get this the same results. It's one of the quality controls that we perform. Yeah, absolute permeability and porosity. You can correlate directly to the plug, to the subsample in plug scale, with no further issues.
So did you make like correlation, and did you find some matching between them?
Yes. They match for sure. Yeah. Here, I have in the next presentation, but I have some comparisons. You can see this one here. It's a publication that we published last year, and I have some values. For example, this one here, we have a absolute permeability of 600 millidarcies, and we got the same value in using PNM. Okay,
So
it matches.
what's the scale here? The vertical scale, body BW. What does that mean?
Yes, it's a pressure. Yeah, it's Pascal. Yeah, I insert a really tiny pressure drop here, and just to give an idea what's going on there. But match perfectly. I can tell you, not only porosity but also absolute permeability, formation factor, elastic properties. It's you can perform this kind of evaluations here that I mentioned before, and all of them, they are pretty much it's part of the quality control to check absolute permeability with this, but it's also some kind of direct result. Yeah, you can once you can control your simulation, if you get the porosity absolute permeability, you can move on for the other analysis.
So were both of them having the same scale, like a scale of measurements between the plug and the pore network analysis?
Mm-hmm. For example, on this one here, I just took a small subsample, okay? Dropped the sample and did this kind of evaluation, the numerical experiment. This one here, I perform a plug. Can you see? It's the reconstruction of the entire plug. For example, some of the methods, computational methods, it's not possible to do directly in the whole plug, but you can perform in some specific regions, and you can perform this kind of scaling procedures to get for the whole plug, and they match perfectly as well. Okay, it's a numerical approach that you can correlate several different regions, and you have this kind of pattern, yeah, for your whole plug. Yeah. But it's possible. It's possible from the subsample to entire plug. It's possible to perform this kind of evaluation.
Yeah, actually what I mean that if we measure the permeability from a plug or from the whole core, it will be the measured scale or the scale measurements around a few inch. However, if we measure the permeability from well test analysis, it will be like few meters or reach to 30 or 100 meters. So there is different scale. So what about the distinct scales between core plug and pore network analysis? Do they have the same scale or similar or somehow similar?
Yeah, in this case, it's a different workflow. As I mentioned before, you have different workflows according to each analysis that you are performing. In this case, if you are interested in the whole core, there is a specific workflow that you can do this kind of acquisition of the whole core. You can perform this kind of plug selection, and then you can move to the simulations in the microscale, pore-scale, and then it's like a downscaling and then upscaling again. Yeah? With this kind of results, you can correlate with your whole core. You have this kind of log profiles, and it's also part of the digital evaluation. Yeah. Today, I just show you some of the basic concepts that from the reconstruction, if you have this kind of representative elementary volume, some of the methods that's possible to perform, but this one, it's part of the what I call the new frontier, that we already have published material, and you are correlating from the whole core acquisition. You're selecting some regions and samples. You're performing some lab experiments as well, And then we are analyzing the pore-scale phenomena and then correlating to a larger volume until you get again the whole core. Yeah? So it's like a different workflow, but it's using some of these techniques here, some modifications in some aspects, but it's possible to perform. And we have really good matches as well. Yeah.
Okay, so what about the field scale evaluation or field scale application of the pore-scale evaluation? Is that possible in the field application?
So you're talking about the log scale to the field scale. Yeah?
No. I mean, if we consider this technique of pore-scale evaluation in order to get useful from it for field application, like what we are working now in the fields, we use the permeability, porosity, we got them from like core plug, from well logging correlation, from well test, maybe some other parameters from seismic. So they are the main sources, the most popular sources to get these petrophysical properties. So is pore-scale evaluation technique applicable in the field?
Yeah, actually, we have some capabilities to do this, to correlate this kind of log profiles and some of the whole scale, whole core micro CT, sorry, whole scale core CT acquisition, the images. We can generate some profiles there numerically, and then we can correlate with the logs that you have, and then we can perform this kind of scaling, for example, for the plug for a larger core. It's also possible. As I mentioned, it's a new frontier, but a lot of things have been done so far. So, of course, if you're trying to link in there for the circuit, for example, to the field scale with some other specific information, some methodology, some workflows are still development, okay? But it's possible, yes. Tomorrow I will show you some case study from England, Middle East, and they performed this kind of evaluation from the whole core, yeah, from some of the logs that they have until the covering the microscale application, some simulations, some correlations, generation of PCKR curves, correlation gave some kind of K-phi trends, some of the information that they got from the medical CT scan of the whole core, they can perform and try to correlate with the log and the logs. And it's really, it's a part of the digital rock as well. It's some of them are in development, some of them are really well stated, but for sure it's part and will help you a lot in the near future.
Okay, so my last question: how is the cost of this technique in comparison with the regular measurement of petrophysical properties in the lab? Like, is it expensive? Is it economically applicable?
I can tell you that it's economically applicable for sure, and not only let's say regarding the values, but also in the how much time do you spend to perform this. Yeah? Sometimes you have to perform, I don't know, several hundreds of measurements. Some of them were selected for a skull procedure. Some of them you discard. And then here you can do in a fast way. Yeah? You can perform this kind of acquisition check. You can simulate all in parallel with lab experiments, for example. As I mentioned before, some of the experimental measurements you have to consider when you are performing digital one as well, because they are doing this kind of quality control, or at least they help you to verify if all your measurements or estimation, if they are correct. But I would say it's perfect match with, let's say, a value, and it's not only regarding money, but also time. Yeah? So we are saving time and money, but for sure, it's applicable nowadays. As I mentioned, I work for Halliburton Brain. We have performed this for several years. And some of this development, some of the case studies, they are already published in the last few years. So there are several things happening. Yeah. I'll show you tomorrow one of the papers from this year, the beginning of this year, regarding this complete workflow regarding the macro samples until the micro sample, and then correlations and some understanding of the fluid flow process there. This kind of changing wattability and we're going to see it, but then you can correlate again, and you can see this kind of correlation to a log profile. And then this can give you some ideas of what you can do for the larger scale, yeah? If you're considering reservoir simulator. Yeah?
Okay, I'm done with my questions. If anybody has a question, he may go ahead. Maybe from your side, audience.
I know it's a lot of information. It's not so simple, the whole workflow, but if you are interested in some of these steps, or I don't know if you have some questions, or you want some reference, yeah, I can give you just an email. I know some people here from Brazil that you are watching that they have a lot of experience as well in some of these steps here. If I don't know the answer, I can ask them and I can discuss and then send you an answer, okay? Feel free to contact me anywhere. If you want some academic reference, send me this mail here. If you want to take a look at what Ingrain can do, you can contact me for this mail here. We have a lot of researchers, consultants in both in the company as well.
Okay, so if nobody has a question, we can skip now for today, and we will meet tomorrow at the same time. It will be 9 a.m. for your timing, 3 p.m. our time. So thank you very much, Dr. William, for your nice presentation. And thanks for everybody who attended this presentation, especially the audience from Latin America. We will
Thank you all. If you want any questions, if you have any questions, or just send me an email, okay, as I mentioned. And thank you very much for this opportunity.
Okay, thank you. Bye-bye.